All right, quote of the day we've got up here by Mr. Smith. Not Alex Smith, Adam Smith. APEC. All right. We learned most of what we need to know about bonds. This will be a little bit of review. But these are some cool bonds called coordinate covalent bonds. A coordinate covalent bond is also called a dative covalent bond. It's a covalent bond in which both electrons come from the same atom. So instead of sharing, I share one, you share one, they both come from the same atom, and that's why it's labeled a little bit differently. So if you have BF3, for example, BF3 we know is, again, stable. It's an exception to the octet rule, right? Yeah. What would the shape of BF3 be? Trigonal planar. Would it be polar or non-polar?
Non-polar.
Non-polar, because all of the S dipoles would cancel out. Now, is this a good drawing of shape?
No.
No, it's not. Okay? That'd be a Lewis dot structure without all the lone pairs around the F. So that's an issue. But you take that and you add this together with ammonia, NH3. An interesting thing happens in the NH3. The lone pair from the ammonia, from the nitrogen, makes a bond with the boron, and now it fulfills the octet rule with the boron trifluoride instead of being an exception, and the NH3 connects together. But you'll see this nitrogen here now has 4 bonds around it. Okay? 4 bonds around it. It tends not to have 4 bonds around it. But this is called a coordinate covalent bond with ammonia attaching to another substance. This is the dative bond right here, the bond between the boron and the nitrogen, because the 2 electrons are coming from the nitrogen to make that bond here. So that's how they kind of stick together, so to speak. Yes? Yep.
Is it normally nitrogen that does it? Is it odd?
Nitrogen does it a lot, yeah.
And would like aluminum do it like this?
No, usually things, when we talked about coordination complexes before, it's usually things that do that, like water can do this type of connection sometimes. Ammonia could do this. I'll show you an example of this in the next slide. Here's chlorine can also do this. Okay, so here's cobalt with 4 ammonias and 2 chlorines. Okay, and this is called a coordination compound. So when you have a complex ion and a counter ion, you can make this coordination complex is what it's called. So that's where the idea or the naming of coordination complexes come from. Yeah?
So in this case, would the cobalt be the counter ion?
Cobalt is the metal ion bonded to 1 or more of the ions. So this here, let's see if I can clarify what that would be. It's not clear. Let me see if I got it. You get the ligands are on the outside. So this whole thing is the complex ion, and then the counter ion would be something that goes with this. Complex, yes. Yeah, no problem. These things on the outside are called the ligands. So here's our metal cation, the ligands, and if you attach these all together, you get the complex ion, and then the counter ion is meant to have it be a neutral solution or compound. A ligand has at least 1 unshared pair of valence electrons. So chlorine had multiple pairs, NH3 had 1 unpaired. On this example. So water makes a good ligand, ammonia makes a good ligand, chloride ions, pardon me, not chlorine, the chloride ions. So this chloride ion is donating both of its electrons to that cobalt connection here. So that's why halides tend to be pretty good with making ligands. Carbon carbon monoxide is also another one that makes ligands pretty easily. And that here is due to the polarity of this molecule here. Which one, carbon or oxygen, would be more electronegative? Oxygen would be. So our dipole would be pointing in this direction. So you would tend to have a lot more negative charge on this side and a little positive charge on this side. And so that could cause an attraction for the carbon monoxide to attach. Another molecule that it can attach is oxygen, O2. O2 has the ability of attaching. It's not as likely, but this is why carbon monoxide and oxygen, O2, are sometimes replaceable in many places, especially in hemoglobin in your body. The oxygen that it attaches there can easily be detached due to its properties, and that's how hemoglobin can carry the oxygen around in your body. If you breathe in carbon monoxide, it takes the place of that oxygen, and when it takes the place of that oxygen, it doesn't have the same chemical characteristics, and it doesn't allow your body to breathe, so to speak, your cells to work. And so that's why this is such an incredible toxic chemical, carbon monoxide. But it still can be a ligand, and that is one of the things to be concerned with coordination complexes. Now, some theories of bondings. There's multiple theories of bondings. Again, remember, bonds are all human invented. There's lots of debate over what's the best and what's not the best. But we want to try to get a picture of what's going on, and usually these theories have to have evidence about the properties to back them up. The first one is called a valence bond theory. This says that if you have a p orbital and you have another p orbital, and they're each half filled, they can come together and share those electrons and make a full orbital. These two orbitals come together to make one filled space, which is called a sigma bond. So that's when the two electrons come together and they're in the same space. The second theory is what is called the molecular orbital theory, or the MO theory. And in this one, it's a little bit different. You take the two atomic orbitals and then you combine them together. And what happens is they form a bonding orbital called sigma 2p, then they form what's called an anti-bonding orbital, where these two don't actually bond at all. So it's a way of explaining some of those nodes that we talked about in quantum mechanics, and this is one theory that's commonly used to predict where the bond will form when these two p orbitals come together. Usually, people can see this easily. You just blend them together, squish them together, you get a bigger thing in the middle with the two electrons, and we're good to go. Usually this, you go, wait a minute, why anti-bonding? Yeah, so that means they're just not facing the right direction to share properly. So they don't actually bond. And so you either have this or this. Now, the good news about the molecular orbital theory is the AP test doesn't test it. That's the good news about it. So, they do test what's called the valence bond theory. So what you need to know is based on the valence, electrons, the Lewis dot structures, and how they come together. Yes?
Well, orbitals being on the midterm, not necessarily this lesson, but orbitals.
Not this lesson, correct. Orbitals in general will be on the midterm, yes.
This whole PowerPoint will not be on the midterm.
Correct. They will not be on the midterm. This PowerPoint will not be on the midterm. What's on this PowerPoint will not be on the midterm. However, the concepts that are in this PowerPoint are mainly reviewed. But the advanced topics on this will not be on the midterm. Yeah?
We had a PowerPoint for the last midterm. That was basically just a page with all the stuff.
Oh?
We have another one.
Yeah, I'll show that at the end here. Just remind me if I forget it. I have it, I just have to find it. Now, this theory is no longer covered on the AP exam. But again, they're just different ways of approaching how the orbitals come together. Okay, the valence bond theory, which is on the AP exam, says that electrons in a molecule occupy orbitals of the individual atoms. Stable molecules form when the potential energy of a system is minimized. So we're trying to minimize the potential energy. Atomic orbitals overlap to form bonds. So the p orbitals overlap, you can get a bond. If an s orbital and p orbital overlap, you can get a bond, is the general idea. To accommodate bonds, though, valence orbitals of the central atoms combine or hybridize. So the combining is you got two p's coming together, it makes a bond in the p orbital. Hybridize is a little bit different, but it's the same idea about the orbitals coming together. They just do some different things to explain what happens. So a sigma bond forms as orbitals overlap. So if we take two 1s's, we overlap the orbitals. There's our hydrogen sigma bond between two hydrogen atoms, making H2. This hydrogen shares an electron. This hydrogen shares an electron pair. So the electron density between the two atoms, this here is representing the sigma bond with the electron density diagram shown there. So that's a simple bond between two s orbitals. Yes? This here, yeah, each of them was a 1s. This 1s is representing the actual orbital, not the number of electrons. So this is the 1s orbital, represented by a box. It's not telling you the electron configuration of it. So when you see a code underneath it that doesn't have any numbers on it, it's just telling you what orbital that box represents. Yeah. So hybridization is the mixing of two or more atomic orbitals to form a new set of hybrid orbitals. So you mix some atomic orbitals together and you get a new, what's called a hybrid orbital. Mix at least two non-equivalent atomic orbitals, S and P. Hybrid orbitals have very different shape from the original atomic orbitals, so the shape is modified when this happens. The number of hybrid orbitals is equal to the number of pure atomic orbitals used in the hybridization process. So what we're doing is we're changing the shape of some of these orbitals. Covalent bonds are formed by overlap of hybrid orbitals with atomic orbitals. So the hybrid orbitals overlap the atomic orbitals, and you get these bonds that occur. Overlap of hybrid orbitals with other hybrid orbitals will give you these bonds that occur. So a hybrid orbital is just a modified shape that accommodates reality. It actually is a better model because it actually shows what the shape is of these molecules. So C and H, for example. This here is the orbital diagram for H, and here's the orbital diagram for C. And if you look at this, carbon only has two unpaired electrons, 1, 2. So it should form only two bonds with hydrogen. 1, 2. Two hydrogens are coming in, right? And how many hydrogens combine with carbon? 4 to make methane. And carbon also likes to have 4 bonds. Now, how do we know it likes to have 4 bonds? Well, lots and lots of observations tell us that. As well, it has 4 valence electrons. Now, one thing that we may not have talked about is there is a hint that sometimes works really well. Okay? Anytime you're dealing with hydrogen, oxygen, nitrogen, or carbon, all you have to do is remember the honk, 1, 2, 3, 4 word. Hydrogen always wants to have 1 bond. Oxygen always wants to have 2. Nitrogen always wants to have 3. And carbon almost always wants to have 4. It's really cool because it works most of the time.
Yay! Most.
Why
can't chemistry be 1 plus 1 equals 2 all the time?
So honk 1, 2, 3 was what I go to first. It almost always works. And then if that doesn't work, you can go on to the octet rule. Start having a fun time counting. And then if you get to that point, it doesn't seem to be working out, then just you got to consider the exceptions to the octet rule. What's up? So honk 1, 2, 3, 4. Hydrogen has 1, oxygen has 2, nitrogen has 3, carbon has 4. Now, why would that be so helpful? Okay. The cool thing about it is you could draw structures involving hydrogen, oxygen, nitrogen, and carbon. As long as it follows the honk 1, 2, 3, 4 rule, the structures will be correct. Works really well if you are a biochemist. Okay? So, awesome. All right, so if we look up here, this is the theoretical prediction for CH2. 90 degrees, C, an H, and an H. Okay, that's what we would predict based on electron, electron, pair up, electron, electron, pair up. The reality is very different. Our reality is this, what's this shape called? Tetrahedral shape. So we saw this tetrahedral shape, and all electron domains prefer to be as far apart as possible. And the angle was 109.5 degrees. And that's methane, and that's the basic shape of all organic molecules. This tetrahedral basic shape. So the question is, why does it form 4 bonds? How does it form 4 bonds? What is going on? So, how is it forming 4 bonds? We know its shape looks something like this. So for carbon, let's draw out really quickly. Carbon's got how many valence electrons?
6.
4, 6.
4.
4. All right, 4 today. So we draw them in. 2 in the P. 1 up, 1 down. It always has 4, but that's okay. In the P, we got 1 up and 1 up. There we go. All right. Now, the cool thing is, in order to form 4 bonds, you have to first rearrange the electrons. So, instead of having these 2 paired up, you put 1 up, 1 up, 1 up, and 1 up. Remember the electrons, they don't like to what? They don't like to be together unless they have to be. So, if we could somehow rearrange them, that seems to make more stability sense. And what that does is it creates this structure here. These 4 are now put at a new energy level. Okay? And these are called sp3 orbitals. They are at all the same energy level. So if this was energy, usually S is lower than P. Here the sp3 are all at the same energy level. Same energy level. So if you look at this here, this is a way that hybrid orbitals rearrange the electrons, then rearrange the locations. So here's another way of seeing it. Okay? Here's our energy graph. We got 2, we got 2. What they do is combine together, electrons spread out, turns into the 2sp3. And the energy of that is less than the 2p and greater than the 2s. So this is energetically more favorable because it's at a lower overall energy. So this is why carbon with 4 valence electrons, this is believed why, or explained why, using the models we have, that it is the most stable structure. Yeah. The ZF. Very good question. So for the ZF, would it be considered to have 2 or 4? ZF formula. I think we are using the formula that it is considered to have these 2 on the outside and the rest on the inside for the RZF formula. Some people have debate over ZF that they don't count. They count only the ones that are inside of that, but that would be counted for a normal carbon. There's 2 outer electrons. For the ZF calculation, there'd be 2 outer electrons. The problem with carbon, as you can see, is it readily hybridizes and is found as many different hybrid orbitals. So the ZF issue on that is not the only predictor we have. Now, when it combines together with the hydrogens, okay, it makes the 2sp3, combines together with each hydrogen individually, And this is why you can have CH4 with all of them being paired up. There are 4 sigma bonds form. Okay? SPPP makes sp3. And there are 4 single bonds, sigma bonds, between the carbon and the hydrogen. So this is what it looks like again. These are different energies. This is at a, not quite midpoint, but it is more energetically stable. That's why hybridization occurs, or at least that's the theory. So this is an s orbital, that's a p, that's a p, that's a p. When they get hybridized, this is what sp3 looks like. This one, this one, this one, and this one. You notice the 2 sides are not the same, right? You got one side that has a larger area than the other side, larger volume. When you combine them together, okay, you get the sp3 hybrid orbital or the tetrahedral shape. So that's at least the model. That's why they believe it's 70 degrees, and this is where the electron domains prefer to be as far apart as possible comes from, is based on this hybridization model. Because they have to somehow connect to other C's and other CH4 type things and connect together, and there's molecular shape and structure that's determined based on this property. Now, what if you had something where carbon only bonded to 3 atoms? Only 3 atoms, not 4. So this is not on your notes. This is an easy way of seeing it, though. Carbon is still up, down, up, up, right? 4 valence electrons. You rearrange the electrons so it will bond to 3 atoms. So here, up, 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 up. Now, it only bonded to 2 here, so we will rearrange it so it would bond to 3. Now, 3 things want to connect to it, so we've got room for 3 things to connect here. But the problem we have is we've got 3 identical, what are called sp2 orbitals. In this case, we were told it bonds to 3 atoms. So what ends up happening is this one here, this last one is going to be a p orbital. So let's show you how that works here with this diagram. See if I can get it a little clearer. So the locations change here. So now you can have bonds at each of these locations, and the P, this P is actually separate from the sp2 hybrid orbitals. This gives us a different and modified shape where these 3 put together give us our trigonal planar shape. And this extra P here, can be put into the double bond. So if we have, for example, carbon in the middle, double bonded to oxygen and hydrogen, this has a trigonal planar shape because you have the sp2 bonds all here, and then one of these will represent the bond in the p orbital. So we look here at ammonia, NH3, different central atom. Instead of being carbon, ammonia, you got 3 H's connected to it. Your electrons come in, now it's completely filled up. If the bonds form overlap of 3 2p orbitals on nitrogen, with the 1 s orbital on each hydrogen atom, what would the molecular geometry be? So in this case here, you've got the p orbitals overlapping with all of the s orbitals, we would predict the angle would be 90 degrees, but the actual angle is 107.3 for the NH bond angle. What is happening here is what's called sp3 hybridization. Okay, the N atom in NH3 here has the hydrogens around it, and here it looks just like the tetrahedral, except it's got a lone pair up there, making our NH3 ammonia molecule. It predicts the correct bond angle, and it also allows for the lone pairs to be in one of these sp3 hybridized orbitals. If you have H2S, it needs two bonding orbitals on S to bond with H. So the predicted angle here if it was just like this would be the predicted shape, 90 degrees. But we know the angle is not 90 degrees with a bent molecule. So how do we get the actual angle? What do? We hybridize them. So here you've got 3 sp3. There's 2 that are lone pairs and 2 that are unpaired. Okay, the 2 that are unpaired now can accept hydrogens. Those are the sigma bonds. And the 2 that are unpaired are lone electron pairs. So to predict the hybridization on the central atom, we first draw the Lewis structure of the model, count the number of lone pairs and the number of atoms bonded to the central atom. That equals our steric number. Our examples here is if you have a steric number of 2, you're going to have sp hybridization, such as beryllium chloride. If your steric number is 3, sp2, boron trifluoride, trigonoplanar shape. Steric number is 4 is sp3, which is tetrahedral shape. Okay, tetrahedral electronic configuration. And then sp3d and sp3d2 are the hybridizations. Now we went to steric number 4. We went 4, 3, and then 2. Some review of our geometries. Here it is with our hybridization put in. Here's sp, sp2, sp3, sp3d, sp3d2. This is the octahedral. This is the what shape? Trigonal bipyramidal. There we go, octahedral, tetrahedral, trigonoplanar, and linear. And then you'll notice the shapes come off of it with the lone pairs. So where do we get the 2 identical sp orbitals from? We've got our carbon again. Okay, if we had carbon, for example, rearrange the electrons, 1 in each. If it bonds to 2 atoms, there we go, atom 1, atom 2. Okay, what do you have to have in order for it to bond to 2 atoms here is you're going to have 2 p orbitals and 2 sp orbitals.
So I thought that the 2 p atoms are the ones with just 1 arrow by itself. Or is that the sp?
All of these, this is carbon with 4 electrons. All of them have 1 arrow right now by themselves. In this case here. And then we're saying we're sharing with another atom here. So we need to look at the P ones. Why do they share with the sp and not the p? That's a good question. Why not p? What's up with p? Okay, why don't they just share with the p? So let me see if I've got a picture of this here. Okay? An SP happens when the S and the P mix together. And when that happens, you will have two different 180 degrees apart positions that could be shared. Okay? P orbitals go, this is an SP, 180 degrees apart. The P orbitals can go up, they can go sideways, they can go in and out of the board. You also have one that goes in and out of the board and one that's going up and down. Those are the P's. Okay? Let me see if I think I have a good picture here of one. There it is. So this is why the sp bonds here with beryllium and chlorine. Okay? This is the sp that's connecting of the two. The p is actually not connecting in this case with the beryllium chloride because there's not enough electrons to fill the p. There's nothing in the p. If you have carbon, you're going to have some electrons in the p.
Okay, so that's because SP is lower than
Yes.
or
Exactly.
okay.
SP has less energy. Now, if we have something like PCl5, okay, you want to draw the Lewis structure of the molecule. Steric number is 5, so 5 orbitals must hybridize. And that's what's called sp3d. What this looks like in phosphorus, you've got one extra electron, so it goes into one of the d orbitals. 5 sigma bonds can form, and sigma bonds are what we normally think of as the single bonds in general. The next one here, okay, is arsenic pentafluoride. Again, you have the sp3d sharing here. Here is one that is seesaw shaped with the lone pairs. In sulfur, you can get sp3d2. So you have the, look at these, paired up electrons. So we were talking about the, wait, aren't they paired up? These two have to be separate for hybridization. So you take 2 more orbitals. And therefore 6 bonds can form. This is why sulfur can have the octahedral shape. Now, we've been focusing on the sigma bonds. The last type of bonds are the pi bonds. And it sounds like we need to do something different, so we're going to stop where we're at with pi. Yay!
She's bringing pie. Everyone's bringing an XL pie. We'll have like a pie set. I'm not even kidding. You said every day
All right, ladies and gentlemen. F and G. I'd like you to do F and G. F and G, please. Let's talk about it. No, it's just a harder problem. You will not have on your quiz. Good thing to think about.
Wait, will this be on the recording?
Yeah. Okay, if you need a blue sheet, they're here. All right, let's look at just ideas on F first of all. F, there are two possibilities. It could be a double displacement or it could be a redox. Okay? A double displacement is when, again, the ions are switching. Redox is when the electrons are changing. So to know if it's redox or not, what do we have to look at? One, solubility. That solubility usually tells us if it's a double replacement. So you look at solubility first. Is it precipitate forming? Is it gas forming? Is it weak acid forming? The answer to all three of those is no. Then the next thing to look at is the reduction potential table. And that's going to tell you how it will become a redox reaction. So those are the steps on something like F. On something like E, okay? Something like E, we again didn't do E, so we're going to talk about that. That would not be on the pre-quiz tomorrow. We will talk about it. The actual quiz. Sorry.
We took a pre-quiz.
Pre-quiz. So, a couple more minutes, and then we'll check our answers. See how we did. Yeah? Oh, usually when you have an alkali metal being placed in. E is not going to be on the test tomorrow. We will do it later. You don't have to do it now. All right. So, looking at the answers briefly, again, you can look at this online as well. The chromium 2 chloride, okay, chromium goes from 2 plus to 3 plus. Fe goes from 3 plus to 2 plus. And again, the chloride and the sulfate are spectators in that process. And then in G, we've got our, again, balancing the equation. We know it's acidic, so we didn't have to change anything when we got to the end. We got the potassium permanganate ion going to Mn2+, similar to our lab, if you remember. Knowing the permanganate and the chromate dichromate combinations are very helpful for predicting reactions. This one up here is a redox equation as well. We did not do that because it will not, that level of question will not be on the quiz tomorrow. It'll be like something like this or something like this. Top one is redox because copper is losing electrons to become copper 2 plus. And this PowerPoint will have some extra practice questions on it. You're welcome to do.
Can you put up what you did in the exam?
Oh, the exam?
It tastes okay, but then